Okay, so let's say we're given this heat equation with the boundary conditions and this initial condition, and let's try to solve this, right? Now, usually they come with some conditions for x and t, but it's not too important. So this will be true for positive time, and x would be between 0 to 2, because see, it's touching ice at 0 and 2. So what you have is a one-dimensional rod, let's say 2 meters long, and it's touching ice, so the temperature at both that points would be 0. Okay, and initial condition is 2x minus x squared, and the graph of that is an upside down parabola that's like that. Okay, and if we solve this, we'll get some solutions, right? So here x will be between 0 to 2, and this will be t greater than 0. So there's some conditions for what x and t are, but that's not really important. We just have to pay attention to this one. Okay. So how do we solve this? And I have to reiterate this philosophy that when it comes to PDEs, we don't solve them. What do? We guess. We make educated guesses, right? So we come up with some building blocks, and hopefully we can use them to find the final solution. That's our idea. And the way we do it is by first thinking of this part only. Okay? So we want to throw this in later. Okay? So it's just like how you solve the second order ODEs with initial values. You solve the general solution, and then you match the initial condition using the conditions. You get the value for C1 and C2 by doing that, right? So that's what's going to happen. And when you solve this, we are also going to look for the simplest building blocks. So one thing that these conditions enjoy is that if you have any two solutions of this and this, then some of the two solutions will again be a solution. Or any linear combination of the solution will be again a solution. So linearity makes differential equations a lot easier to handle, because that allows you to start coming up with some building blocks, and then later just take the linear combination of everything, and then you get the general solution from it. Okay, so what kind of building blocks are we looking for? We're looking for the ones that look like a function of x only times a function of t only. Okay. Sometimes I write f and g for it, but then it's confusing. So let me just write capital X for the function of x, capital T for the function of t. Okay. So we want to look for all possible non-trivial solutions of this system that looks like this, so that once we find all of them, then we can just take the linear combinations of them to write down the general solution that will solve this one, and then you can apply this one to figure out the coefficients that actually solve everything. Okay. All right. So we just look for that one. Okay. Now let's plug this into the left side. By the way, this sub t means partial derivative with respect to t. Xx means second partial with respect to x, right? So what would this evaluate to? What's ut then for this one? It's a partial derivative, which means you don't do anything to the x, right? This is a constant multiple, right? So you just get t prime of t, right? Okay, what is uxx then?
X double prime x.
Mm-hmm.
And just tt.
Okay, so we plug that back in here, and we get xx t prime of t equals to k times x double prime of x t of t. Now okay, so you have this, and right now it doesn't seem to be saying anything at all. And the first person who thought about this must have been a genius. Someone came and said, try dividing both sides by kxt. So we're going to divide. So this is a crucial step where if nobody tells you to do this, then you would never think of it yourself. Okay? So we divide both sides by kxt. And then simplify, which gives you t prime of t over k times t of t equals to just x double prime of x over x of x. Okay. So you have a function of t on the left side, which does not depend on x, right? And you have a function of x on the right side, which doesn't depend on t. When can such a thing happen?
Both be constant.
That's going to happen only when it's a constant, okay? Now, if you're not convinced, think of it like this. Just plug in 0 in here, that's going to give you some value, right? Then you can plug in t equals to 1, 2, 3, 4, whatever, and all of that has to equal to x double prime 0 over x of 0, right? Regardless of what you plug in t, right? So we see that whatever value you plug in here is going to equal to x double prime of 0 over x of 0, which is some fixed value. So we see that this is a constant function. Okay? And you can reverse this role. You can plug in 0 here, and then just change x to be an arbitrary value, and you see that all of these should be equal to some constant value, which is t prime of 0 over k times t of 0. Right? And therefore, we can argue that they both have to equal to a constant value. It has to be a single number. Okay? Now, for the ease of later calculation, we're going to put a name for this constant. We're going to call it not lambda. We're going to call it negative lambda. Okay? You'll see later. Okay. So, so far I expressed three ideas. First, we look for building blocks that looks like a function of x times function of t. And then when you plug it in, you want to do this crucial step of dividing by kxt. Then suddenly you can make an argument that this has to equal to some constant, and that one we're going to name it as negative lambda, right? Okay. Now let's apply these two. I said we were going to apply this one with this one. So for this one, we have u0t equal to x of 0 t of t, and that has to equal to 0, right? Okay. Which means either x of 0 is 0 or t of t equals to 0. Okay. What happens if t of t is 0?
U becomes 0.
Huh? It becomes?
U becomes 0.
U becomes 0, which we call the trivial solution. But our goal is to find building blocks, the non-trivial ones, right? So we don't like that. T of t equals to 0 gives you a trivial solution. That's not going to do anything. I mean, we already know that 0 satisfies all of these trivially, right? 0 would satisfy this condition easily, right? And these will be also satisfied. So 0 doesn't add anything to the knowledge that we already have, right? So we don't care about this one. It's going to give you trivial. So we only want to track the case when x of 0 is 0. Now, u of 2 of t equals to 0 would mean x of 2 times t of t equals to 0. And for the same reason, we would get x of 2 equals to 0. Okay. Oh, that gives you two endpoint conditions for x, right? Uh-oh, now it looks like something that we've done before. Since we have something for x, we better go back and try to see what x could be, right? Let's multiply x both sides and rewrite this equation. This equation will be x double prime equals to negative lambda x. Okay? And then x double prime plus lambda x will equal to 0, with the condition that x of 0 is 0 and x of 2 equals to 0. And our goal is to find out all the possible non-zero solutions that will satisfy this. What is that?
What was that? I'm sorry.
What's the solution to this? Now, can we find non-zero solutions of x for any lambda?
No.
No. Only when lambda is equal to?
0 or possible?
No. Well, okay, that's true, but we are more specific than that. We already solved this a few lectures ago, right? What was the solution? Actually, I did it yesterday. N squared over pi squared over 4, right? And then the eigenfunctions were x of x equal to sine n pi over 2x, right? Okay, with n from 1, 2, 3, and so on. Right? In other words, what you have here is the Sturm-Liouville problem. Right? That's why we solved that equation. Okay? Yeah. I actually solved this yesterday. Well, the only difference is yesterday I had this as y double prime plus lambda y equal to 0. Y of 0 is 0 and y of 2 is 0. Right? But the solution is the same. It's this. Right? Yeah. Lambda would be this and x would be this. Okay? Now, since we figured out the value of lambda, now it's our turn to find the t. T prime of t over t times k is negative lambda, but lambda is n squared pi squared over 4, right? So we multiply this to the other side. Okay, so I'll have to erase this. And we get t prime of t equals to negative k times n squared pi squared over 4 t of t. And that's a separable differential equation, right? So let's see if you know your ODE well. Y prime equals to y. What's the solution to this? What's a function whose derivative is same as itself?
With the x.
E to the x. So the general solution is this, right? Okay. What if I have y prime equals to 2y? What's the solution? Either 2x, because if you differentiate, 2 comes down. So it's like this, right? Yeah.
So
If
you're
you
saying
have...
reciprocal? Is that
No, it's a...
No, just
No, if it's 5y, what's the solution? 5x, right? Just plug it in, you see that it works, right? If you differentiate, if you plug in here, that means you differentiate. The chain rule immediately pops up a 5, so the two sides will be equal. You see it? Just plug it in, you'll see that it works. Do you agree?
so we found dt?
I mean, and then look at this. This is exactly like this format. You have t prime equals to some constant times t, right? It's exactly like this. So what's the solution in this case? T of t would be
E to the
some
negative
constant
k,
times
etc.
e to the negative k n squared pi squared over 4 times t. Now, if you can't think that on your own, what you could do is you can do the following. You can just integrate both sides by t. That would be another way to get it, but that would be too time consuming. You know that f prime over f integrates to ln of f? Or you can just use t of t as u and do the u substitution. And if that will enable you to integrate this. This will integrate as 1 over k times ln of t, with the u substitution. Okay. And this will be this times t, and you solve for t of t, then you get the same result. Okay? But you don't want to do that when you can just see it and then say, oh, that's the answer. Okay? That has to be the answer. Right? Okay. So what do we find? We found out that if you set uxt as some function of x times function of t, then the function of t will look like that. And function of x will look like the sine. Okay? And this will be all possible non-zero functions that are expressible as a function of x times function of t. We found all of them. Right? Okay. And because this is a linear differential equation with linear conditions at the endpoints, that means now we can just add up all possible things that look like this and get a general solution. So this now implies that uxt equals the sum of n equals to 1 through infinity. N starts from 1 because n is 1, 2, 3. Okay? So n from 1 through infinity. Of these things where c is some constant Cn. Okay? So it could be C1 for n equals to 1, C2 for n equals to 2. So you have infinitely many different coefficients and you add them up. So this is like the general solution. And now we just have to apply the initial conditions. Which means I want now, so this would be like step 1. Okay? Step 1 will be you finish up till here. Okay? Okay, now step 2. So we found out all the possible solutions of the heat equation and the given boundary conditions. Now we have to figure out what satisfies the initial conditions. Okay? So let's try to plug in ux0 here. Okay, if you plug in 0 into t, what do you get here?
1.
E to 0th power, that's 1, right? So this simplifies to just Cn sine n pi over 2x. What's that? And I need this to be ux0 is given as 2x minus x squared. What's that? Fourier sine series, right? It's the Fourier sine series. And we also did the work for that, right? We forgot the value. It was something over n cubed pi cube, right? It was negative 8 n cubed pi cube. Can you check the notes? Is it this one, or am I wrong? We just did it a few minutes ago. I'm looking for the Fourier sine series of 2x minus x squared.
This one is 16.
Negative 16, okay. Over n cubed pi cubed?
Yeah.
Okay. So we got this by what? If we take this one, this value here was the output of 1 over 2 over L from 0 to L. Our L was 2, right? Of 2x minus x squared sine n pi over 2x dx, right? If we compute this with L equals to 2, then this L replaced by 2 and do this computation, we got this value, right?
Right.
Yeah. Okay. So good. These will be our CNs, right?
So now we have a unique solution.
Now you plug that in, then that's your unique solution. I like that word unique because that's true, right? I haven't proved it yet, but if you have these boundary conditions with an initial condition, I can prove that the solution will be unique. Okay? Right? We already know the existence because we have a solution that satisfies all of them, right? But because we're basically making the building blocks and making it satisfy everything, the question would be at the end of the day, is that all the solutions? Maybe there's some other solutions that we haven't looked for. We're just basically hunting for solutions. We're not solving it, we're guessing it, right? But if you can show the uniqueness of solutions, which I'll do a few lectures later, probably after exam 1, you'll see that this indeed will be the only solution, right? Okay. So what's the final answer?
Plug in everything.
Yeah, you just plug in the CNs to this one. That's the solution. Summation n from 1 through infinity of negative 16 over n cubed pi cubed, negative 1 to the n minus 1, then e to the negative k times n squared pi squared over 4t sine n pi over 2x. Now, you can also see that I just left this k as a generic k, but you know, k really depends on the material. Some material will have a high value of k because the heat dissipates much faster. But if you have a non-metallic one, let's say rubber, that's like it's not a good. It doesn't do a good job in transferring heat, right? So this k will be small. So it really depends on the material. Also, the thickness of the bar would also matter, right? So k has to be measured separately. But you also see that if you have a high value of k, then this goes down to 0 much faster, right? So it's going to reach the equilibrium, which is 0, much faster. Okay? So let's say if k is something like 0.1, then it's going to go down slowly, right? And you can actually graph this to observe how the heat would go down. And it does look like the heat distribution going down to 0. So I'll also show you some computer-generated pictures for that one. But that's what we have.